Nice. All right, so our cool down for lesson 7 in our packet, we're just going to take a look at how we could interpret or how we could change and adjust so we have our different time spans. A scientist models the number of grams of radioactive substance with the expression 15 times 1/2 d over 5, where d is the number of days since the sample was measured. After how many days has half of the substance disappeared through radioactive decay? This is looking an awful lot like our setups that we've been using right here, our equation. This is looking like a half-life equation. Hi, this is Susan. All right. Okay. All right, thanks. Bye. That's funny. So our half-life equation is very much set up like this, where we've got our starting amount. Our half-life is our growth factor, so there's our growth happening. We know that means it's actually getting smaller, even though we call it growth. It's growing in a negative kind of manner. And every half-life equation that we've looked at and created, we've used as the denominator of our exponent is the half-life time. How long it takes for a half-life to occur. So that 5 in the denominator is telling us that's how many days it would take for a half-life to occur. If we only give it 1 day out of 5, it hasn't gone through one full cycle. To go through one full cycle in our exponent, we would have to have 5 days divided by 5. So it would take 5 days to make that happen. So we can use that information right there. That 5 days is one half-life cycle. And then question 2 just says, well, after 20 days, will there be more or less than 1 gram of the substance left? And explain your reasoning. Well, if our D is just 20 days, we don't have to change the units. We don't have to do much to this except plug 20 in for D. And maybe when you're going to type this into a calculator, you're already recognizing that 20 divided by 5 is going to put us through 4 full half-life cycles. Well, I don't have a calculator in front of me, but I see that Ellie does, and she is doing some of our calculator work. Ellie, what'd you get when you did this one?
I got 15 over 16.
15 over 16?
Yeah.
All right. So as a fraction, we're looking at 15 over 16. So not a full gram. It's going to be a decimal. Yeah, okay. Oh, did you have it in a decimal form?
Yeah, it was 0.9375.
Nice. So using either the fractional or the decimal point, we can tell that we are less than 1 gram. It is not a full gram. It is less than. So we can explain our reasoning by showing our work and saying that it's less than 1 gram. I was reading a book recently about Chernobyl and the big reactor accident that they had there. And they were giving all these studies about how much radioactive substance is still present in that area of the big Chernobyl explosion and the nuclear meltdown that happened there. So this kind of stuff, it's important, and we still are looking at things like this in our life to know how long a radioactive substance is going to be dangerous. So we know how long before we can start sending people in and taking care of anything that needs to get taken care of. Take a look at lesson 8, cool down number 8. We also had that one, and then we'll take a look at our new lesson 9 about logarithm and what the heck this means. On the day a video was posted online, 5 people watched the video, and the next day the number of viewers had doubled. That right there is looking like a rate to me. That's our growth rate. It's doubling each time. So we are starting with 5 people, doubling each day that we're going through this, and we want to now know how many days does it take for this to equal 640 subscribers. Now we can start some work to get our exponent into something that we can start to calculate. And we would do that by dividing both sides by 5. Right now the 5 is multiplying out in front. So if we divided by 5, we would just have a base to an exponent. Base 2 to exponent d (128), if I did that right. So I need 2 to some exponent to be 128. Is anyone getting close, or are you just like guessing and checking? 2 to the what? 2 to the something? Kelly, what'd you find?
7.
All right, nice. So D would have to be the 7th day. 2 to the 7th power, getting us 128 subscribers. So this would take 7 days until 640 people saw this video. Now, if this trend keeps on going and we wanted to find out how many, starting with 5 subscribers, doubling every day to get to 20,000 viewers, we could do some of that same work that we were starting with, dividing both sides by 5. But taking 2 to some exponent to get to 4,000 might take some serious guessing and checking. A little bit of guessing and checking is a-okay. Has anyone gotten close to an idea? Something about 20,000, or something that would be a little bit more than 4,000? I started with 2 to the 10th power, and that's not enough. Right? 80, did you get something closer than I got?
I did 2 to the 12, and that's 4,096.
All right. So 2 to the 12th, 4,096. I can write numbers too. So 2 to the 12th would put us over that 4,000 that we're looking for. So that would make sense that we would find that first day. It might be on like day 12 that we would have it over that amount. Another strategy that we could use that we maybe don't stress enough is that we could also use our graphing calculator and our table of values. So if you would, on your graphing calculator, if you've got one in front of you, hit the y equals and clear out whatever you have in there. That y equals, hit clear. And if we type in our equation, starting with 5 subscribers, doubling every day. Sorry, I hit the graph button. 5 subscribers, doubling every day, and then raise it up to the x exponent. Now that x button is next to the alpha key. Just reminding you where that one is. So 5 times 2 to the x power, like that. And then let's go look at our table of values. We can push the graph button, but do you see right above the graph button is the word table? So if we do second graph, we would see a table of values. And I can see that on day 0, they start with 5 subscribers, and then it doubles to 10, and doubles to 20, and doubles to 40. And if I'm looking for the day that it's going to be over 20,000 subscribers, I see that happening here, just as we predicted on day 12. So a calculator could also help tell us this information. And from what we started learning yesterday, we actually could also use this thing that we have right here in our next cool down about the logarithm. So if we needed 2 to some unknown exponent to equal 4,000, I think we had a chance to take a brief look at this yesterday, that a logarithm helps isolate an unknown exponent. So if we bring that base 2 to the other side, it would add a log to it. That's the process that we're doing. Log base 2 of 4,000 would actually get our exponent all by itself. Now this is kind of cool because it's going to give us a super precise answer, a decimal right away. So this is what we just barely introduced yesterday. On a graphing calculator, we could go to the math button, scroll down until we have the log base, and enter it in so it looks like what we just wrote. It's a base 2, because that's the base raised to an exponent of 4,000. And we find that's actually 11.9657. So somewhere in day 11, it's actually getting over 20,000 subscribers. So the first day that that would be true would be on day 12. Now, if you don't have a graphing calculator or something that doesn't do a log base, I want to also get you in the practice that we could type it in as log 4,000 divided by log 2. It's like distributing the log, but we'd have to do some division to make that happen. So then we just have a log button, and if you're using something like a cell phone calculator, your cell phone has a log button to it. And so you could do log of 4,000 divided by the log of 2, and we would get the exact same answers going on there. Log of 4,000 divided by log 2. Now this is a brand new concept, so if this isn't quite like making sense, if you're like, what is this all about? It's because we just barely talked about it yesterday. So we'll want to continue that conversation as we look at the rest of lesson 9 that we didn't get to finish yesterday. I'm actually going to jump right down to that cool down for lesson 9, because when we just have this log button on our calculator, the log button assumes that we're working in base 10. And that's because a lot of our world is organized around base 10. This means that we count in tens before we need another digit, right? We count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. As soon as I get to the very next number, I need a tens place and a ones place. And I can count a bunch of 10s going on there. As soon as I get 10 10s, I have to go to the hundreds place. As soon as I get 10 100s, I have to go to the thousands place. So a lot of what we use is in base 10 only because we have 10 fingers. That's why we started counting that way. And everything starts working on base 10. The whole metric system is based on base 10. So when we have millimeters, each millimeter is divided into 10 smaller sections. Ten millimeters, I think it's called a decimeter. And if I had 100 of those, I would have a meter stick, 1 full meter. So metric works on base 10. We in America use the standard measurement, which means we're using all kinds of weird stuff, right? We're like, hey, let's be different. Let's count inches. And then as soon as I get to 12 inches, I have 1 foot. And then as soon as I have 3 of those feet, then I have a yard. Like, we're like all over the place, right? Like, oh, let's do some stuff in base 12, and then we'll do other stuff in base 3, and then for some reason 5,730 feet is a mile. Like, who picked this stuff? I can't figure it out. That part I don't know. But I do know that most of the world works in base 10. So if we were to type into our calculator log 10 without changing any base, it assumes that we want base 10. So these are really nice. I can just push log 10, and you can do this on any calculator too, and find out that it would equal 1, because 10 base 10 to the first power equals 10. Base 10 to what power would equal 10,000? That's what this is asking. That question mark is telling us that. But if we simply type in log of 10,000, because our calculator assumes base 10, I see that that question mark has to equal 4. So 10 to the 4th power, that is a 1 with 4 zeros to it. And 10, base 10 to the 7th power is what our next one is. It tells us the exponent. So it's like we're thinking about 10, and this 7 gets pushed up to be an exponent. Is a 1 with 7 zeros after it. So I know we're kind of jumping ahead to the end of lesson 9, but understanding that a log, the whole point of a logarithm, is to isolate an exponent that's unknown on the other side of an equal sign. So if we had a friend who doesn't know about logarithms, and we're saying, well, log base 10, first of all, that's how we would say that out loud. Log of base 10 of x equals y. Really, to interpret what that is, it means we have 10 raised up to some power y that gives us an x value. A log isolates the exponent by itself. If we wanted to rewrite that in exponential form, we certainly could. Man, you guys have been fantastic. You've stretched really far to the end of lesson 9. Let's take our 5-minute break here, and then when we come back, we'll tackle the rest of lesson 9 that we didn't do, and then we'll start seeing more of these logs in different bases in our next couple lessons. Let's take our 5-minute break though. Stand up and stretch, talk to a neighbor, get a drink of water.